Okay, welcome to class. Okay, first up, a few announcements. Next Friday will be our first midterm. First midterm is Friday. I always do the following every time there's a midterm. I post a study guide, and if it's not on the study guide, it will not be on the midterm, right? It greatly limits the amount of material you have to study for. We cover too much in this class, and that's a good thing, but I'm not going to expect you to know all of that in great detail to be tested on. I'm going to limit it. So by Sunday night or Monday night, I usually have the study guide posted, so you have 4 or 5 days to answer any question you like about it, and I promise there will be nothing on the exam that is not on that study guide. And I usually make my exam, look at the study guide, and just copy it over section by section what you need to study. Second, I'll be hosting a review session from 5 o'clock till 7 o'clock. If you can't make it, it'll be on, I think, Wednesday night. I'll confirm that. I'm pretty sure it's going to be this coming Wednesday night. Yeah, I think it's Wednesday night. If you can't make it, I record that and post it to YouTube like everything else that I do in this class. So you can find that study guide there, or that review session there. You can come with any questions. I won't have prepared materials. I'm just going to show you the study guide and say, what can I clarify? And we'll do example problems based on what you guys ask about. Question in the green shirt?
Will the study guide be more like practice problems or just concepts to know?
It's concepts to know.
Okay.
I think Emily, our TA who's there, in the past, she has posted exams from previous years. Some of that will be useful, some of it won't. I use those on homework questions, so you've already seen an example of test questions. By the time I put it on a homework, I make it harder. I add a little bit. You should see that your preparation on homeworks should make the exam significantly easier than the homework questions. But if you want to feel for what they're like, oftentimes Emily will post previous year's exams, and I'm totally fine with that. Question?
Do we get like a little sheet with like all the equations on
Great question. Yeah, you can, it's closed note except for one sheet of paper. So for each exam we do, you can add one sheet of paper. For the first midterm, you got one sheet, front and back. I don't care if you print it on there and use a magnifying glass. The reason I do this, why do I do this? I've taken classes where notes are allowed, open note, and you waste too much time looking for the answer in your notes. That in this class, you need to have it assembled because the exam will take the full amount of time. That said, I work very hard to make sure that exams are not too long, but you will use all the time in the exam for sure. So bring a sheet of note paper, and that helps you organize your notes so you spend less time looking for it and you're ready just to go. Other questions on the exam real quick? Anything else? Yeah, Jorge? Or Carlos?
Do we have homework due the same week?
There will be a homework due on Wednesday. Let's talk about that. Homework solution for homework 1 was posted last night. The solution for homework 2 will be posted Friday right after class. I've had to wait just a couple days, so I'll be posted on Friday. And homework 3 will be posted right after class, so you'll have 2 days to make sure that your solution was what you thought it was for all the homework questions. Yeah?
And then will there be a homework due the week after the test?
There's typically not a homework due the week after. So if you take a test on Friday, there's not a homework due that coming Wednesday. We have a break those weeks, right? So you have 10 days off. This was left in the class last time. It says Eliza Allen. I don't have an Eliza Allen on the rolls, but if this is a friend or if you know who this is, these aren't super cheap. Otherwise, it's going to lost and found. Okay. Any other questions before we get started today? Yeah, Morgan. If you want your homework back, we used to turn it back in class. We're not allowed to do that anymore. It's actually not allowed to, people can see the score, and that's not allowed. So the only way that we can do it and comply with FERPA regulation is for you to pick it up one-on-one. I don't have the homeworks once I give them to the TAs, but the TAs have them, and we should have it arranged that in any office hours that they should be able to get those homeworks to turn them back to you guys. If not, you can always email me. We can make sure that you have time to come pick it up. Okay. So let's get started today. Before we get started, we have a couple quick announcements from Chris.
Yeah, I'm Chris, senior at MSc. Anyway, so the reason I'm here is to talk about ion flashes and tectons. So question number 1, who knows what ion flash is? What is ion flash? Raise your hand. Yeah.
It's like a joint operation between the chips.
Exactly. So it's a joint operation here in Utah between Micron and Intel to make flash memory. And every single year they host these things called tech talks. Does anyone know what that is? What is a tech talk?
TED Talk is a very inspirational topic, anything about anything.
Okay.
So,
yes, but I need a little more detail. Yeah.
Okay, whatever. TED Talk.
Tech, not tech, sorry.
Not
Tech Talk.
Tech, T-E-C-H.
Oh, I don't know.
Anyway, okay, yeah, that's my fault. So every single year, Iron Flash hosts a competition between the University of Utah and BYU, in which they invite some students from the U to give a short presentation, 5 minutes, on a topic that Iron Flash decides. And they do the same for BYU. And they compare the two, or they invite 2 groups from each university, so there's 4 presentations total, and they award $200 for the best presentation. So currently, they're asking for people to submit outlines for the presentation, and then they will review it, and they'll pick 2 people from the University of Utah to talk, or 2 groups. You can do groups of 2 if you need to. So, I guess the question then becomes, why would Iron Flash do this? Any ideas? Interns, exactly. It's all about networking. Iron Flash gives $200 to the winner, but the $200 they don't really care about. Yeah, they like the rivalry between you and BYU, but what they're wanting to do is get people onto their campus to talk to their employees so they can figure out who would be a good intern. So I encourage you, A, to submit an abstract or an outline to them, and if you don't get it, I still encourage you to attend it because it's a great opportunity for networking. I have a great example of this, Christian Robert. His GPA is just shy of a 4.0 because he got an A- in elite.
Scumbag elite.
Last fall, I don't think he got a single interview, right? Last fall, did he? No. Yeah, fall career fair, he did not get a single interview. Not because his GPA was bad, but because he didn't know people. Emily Timmons, she got an internship at Micron because she knows people. And her GPA is good too, it's not because she's dumb. Anyway, but the point is that networking is super important, and Iron Flash sets this up so you can network with them. So if you're interested in the semiconductor industry, even if you're not interested in it, you should still go and talk to people to try and make connections so that when you do want an internship, you're more likely to get a job. Because grades are not good enough on their own. They can be, but statistically speaking, are less important. If you know someone, you're immediately at a higher position. So that's what this is. I'm going to pass around 3 of these flyers. Take a photo if you want. They're a great opportunity. And yeah, if the last person you get them, just go ahead and keep it. Any questions before I walk out?
Let me just plug what he just said. I've had 2 groups that came from my own research group win this in the last couple of years. And some of them now work at Iron Flash, and it is a great place to work. They pay stupid money. Like with a bachelor's degree, you're making what a master's degree earns on day 1. It's unbelievable what they pay.
Yeah, they pay their interns $26 an hour about. That's the insurance. If you're looking for it, well.
Okay, and if you are a material science student and you want help getting your tech talk ready, I'm happy to coach you through it. All right, that said, let's start with our clicker questions for today. We have a brief reading quiz. The first question is, these will be about phase diagrams since we're starting that chapter. Fix this. First question is, which is a parameter that can affect phase structure? Temperature, pressure, composition, or all of the above? Okay, another 15 seconds. Get your answers in. Okay, we're going to wrap it up. Get your answers in. Phone a friend if you don't know what to put. We're going to close. Not causing great grief if I close this. Okay. People think what? A, B, C, or D? They think. Surprising me how long this takes. Okay. Perfect. Fantastic. I'm doing the reading. Next question. What is a triple point on a unary phase diagram? Okay, get your answers in. Should be pretty simple. Okay, I'm going to end it. Okay. Good. All right, maybe the TAs might have made these almost too easy. That's okay. We want easy questions for the quiz. We just want you to do the reading. And the last question for the quiz today is, a system is at equilibrium when free energy is at a maximum. True or false? Okay, 15 more seconds, get your answers in. Okay, and ending the session there. Definitely false. Okay, so this is good. Okay, what are we going to talk about today then? We've got more clicker questions coming up, but that was the end of the quiz section. Today we left off, and the last thing we covered was we said that electrochemistry is very, very analogous to free energy, right? Delta G had the whole delta G equals delta G naught plus RT natural log Q. And we figured out that we could write something very similar for delta V. We could write that delta V, the voltage that your voltmeter will read, is equal to delta V naught, which comes from the standard reduction potential table, minus RT over NF. N is the number of electrons involved in the redox reaction. F is our Faraday's constant, which I think I wrote previously, 96,500 coulombs per mole. Then you got natural log of the oxidized species divided by the reduced species concentration. And then the key thing we talked about last time was that sometimes you have to raise these to an exponent. Why did we have to raise that to an exponent? Can I ask somebody to clarify why we had to do that? The top, for example, is not raised to the second power, but the bottom one is. Maura, you want to explain why we had to do that? Yeah, because silver's only dealing with one electron, but cadmium is dealing with two. To make those cancel out, we had to multiply the silver equation by 2, and we ended up with a 2 in front of the Ag plus ions. And since it's a coefficient in front, that turns into an exponent in this in our reaction quotient. And then one last thing to remind you guys, if we didn't make it clear before, even though we multiplied this whole expression by 2 to get 2 silvers, we did not multiply the voltage by 2. The voltage stayed the same. In free energy, entropy, you would have multiplied that. You do not in electrochemistry. Otherwise, they're the same. Okay? So now let me ask a question, which is, if we remove metal from an aqueous environment, will this stop all future corrosion? Many of you guys have probably seen, if you leave a tool sitting in a bucket of water all summer and come back at the end of the summer, it's a rusty mess. So the question is, all right, take away the water, will you stop all corrosion? Yes or no? Okay, get your answers in. Will you stop corrosion, yes or no? Is water the only thing we have to worry about?
Are you guys saying if you're stopping corrosion happening in just aqueous environment, or is the metal happening?
Good question. I'm saying, can the metal be corroded even if water's not there? So yes or no. Answers in. Will this guarantee the stop of corrosion? Definitely not. So if water's not the only thing that can corrode it, what else can happen? What else can happen? Yeah, Mark.
Mechanical wear.
You can have mechanical wear. Yeah, we don't always think of that as corrosion. That's erosion. But absolutely, you could think it's kind of similar. It can both of them can ruin your part, right? But mechanical wear absolutely can occur. What about can rust form even if there's no water? If you don't leave that tool sitting in a bucket of water, can a piece of steel rust? Yeah. So what's happening? Yeah, what is rust? Let me pick on. Yeah, go ahead.
What if you were to put a metal completely moisture, no moisture at all, submerged it in mineral oil? Would that prevent all rust from happening then?
Submerging in mineral oil is a great. We're going to talk about that when we get to this wire that I have set up as a demo in just a few moments. So let's circle back to that. Why do you think that would stop it?
Because there's moisture in the air, obviously, that causes that corrosion, so it still is reacting with the metal.
So I guess what I'm trying to draw attention to in this question is that it's not just water that can cause corrosion, which 98% of you said that's the case. In fact, it's just oxygen. Oftentimes it's oxidation, right? Oxidation doesn't have to involve oxygen. It sometimes does. It oftentimes does, right? So we can have it happening just like this, right? If you have your grandma's silver spoons, right? And you notice that she has you cleaning them periodically, it's because you're removing scale. That can be an oxide scale, or in the case of silver, it's actually usually a sulfide scale. Silver sulfide forms on it, right? But it can just react with gas, right? Gas that's floating around the room, it can react with. So this wire, it could be reacting with, this is iron wire, it could be reacting with gas in this room to form rust on the outside right now, even though it's not in water. If it happens in water, it's oftentimes faster, but even just oxygen and air can make this happen, right? So we're going to talk briefly about what are these oxides that form on metals and why do they form, right? So first off, let's write what the reaction would be, right? We know that we've got metal picking up oxygen to form some sort of metal oxide, but we can split that up into oxidation and reduction reactions, right? You're going to start out with metal, which has a 0 charge, right? It's eventually going to become a metal N+, and it only can do that by giving up N number of electrons, right? Meanwhile, you're going to have oxygen, which starts out maybe oxygen 2, so it has no charge. It's elemental, so there's no charge on it. And that is going to become oxygen 2- by picking up 2 electrons, right? So if your metal is what's called divalent, meaning N = 2, divalent is N = 2. And examples are like calcium 2+, magnesium 2+, right? Things that are in the second column of the periodic table tend to be 2+. Then you can just add these two reactions together to get this full one. Sometimes it's not as easy as that. Your metal might be trivalent, like aluminum, right? Aluminum starts out as aluminum metal, I've got these electrons on the wrong side, don't I? I'm sorry. Sorry, science is not on point. Manganese, or metal 2+, sorry. Oh dear, all right, erase this. Metal N+ plus those 2 electrons. I wrote my electrons on the wrong side. If you add 2 electrons to this oxygen, then you become the oxygen 2-. Sorry about that. So aluminum starts out as a metal, and it becomes an ion, aluminum 3+ ion, by surrendering 3 electrons. So in that case, you're going to have to balance it to end up with the same number of electrons, right? Remember, redox reactions, when you add them together, your electrons have to cancel out. So in this case, you'd have to multiply this top one by 3, this lower one by 2, so that you have a total of 6 electrons, right? So this is oxidation. There's a useful thing that helps predict whether or not materials will form oxides or not. Because maybe you've noticed this, that some things, like this aluminum ruler, aluminum, do you ever see rust on aluminum? Almost never, right? Is it there? It's a good question, right? Well, let's go up to our table here, right? Our standard reduction potential. How badly does aluminum want to form an Al3+ ion? Well, Al3+, picking up electrons to form aluminum metal, has a negative voltage, right? So most of the things that you pair it up with, oxygen included, actually it doesn't want to do that. Remember, a negative voltage is actually not spontaneous. A negative free energy is spontaneous, so positive voltage is spontaneous. So this is basically telling us aluminum would like to become Al3+, which basically says, why don't we form Al2O3 on the surface of this, right? Why doesn't it rust? Why do you never see aluminum rusting? Any thoughts? Yeah, Matt. Good guess. Because it doesn't happen, you'd assume maybe somehow it is free energy is going up. It actually goes down. So why don't we ever see it? We'll do Anthony and then Jeff, I think.
Isn't it because it's technically not, like it's right in the, like it's metal technically, but it's outside of the D section, so like, because the valence electrons are arranged differently, it just doesn't oxidize as easily as those other metals. Because it does,
good guess.
There is aluminum oxide.
Good guess.
It does oxidize, it's just not as quickly or in air as easily.
You're close. That was wrong, but it was close. Jeff.
Maybe I've got the words wrong, but aluminum, it
it does oxidize the shell. It's like passive.
Absolutely. Yeah, so if you've read the chapter on the Pilling-Bedworth ratio, aluminum is an interesting example of a metal that actually forming an oxide is very energetically favorable. It wants to form an oxide. But what happens is it forms a layer of aluminum oxide on the surface, and that's what we call a passivating layer, meaning once it's there, you stop the reaction. And the reason you stop the reaction is because imagine this scenario, right? You've got your block of metal, right? You got your metal here, and so it's going to form an oxide layer on the surface. Here's your MO, metal oxide. In order for this to keep on oxidizing, for that layer of rust, right? In iron we call it rust, here it would be aluminum oxide. In order for that, what sometimes they'll call it the scale, in order for that scale to keep on growing, you have to have one of two things happen. You either have to have oxygen ions transport that way, oxygen 2- has to go in through that scale, or you have to have metal ions traveling through the scale outwards to the surface, N+ ions traveling through the oxide. Right? So if your oxide is a really, really dense oxide, meaning there's no like holes like Swiss cheese, it's a solid, coherent oxide that doesn't have holes in it, and if it's not conducive to ionic transport is when ions move through a solid. If it doesn't allow those things, then your oxide doesn't grow, right? Because the oxygen can't get in, the metal can't get out, so it's passivated. That's the case with aluminum. It actually every aluminum you see has a layer of aluminum oxide on it. It's thin, you can't see it, it's very, very thin, but it's there and it actually protects the aluminum underneath. If you take a Brillo pad, right, or like some steel wool to this, you can scratch that away and it'll eventually form an oxide again. You can see that sort of process occur. But aluminum is an example of something that forms a passivating oxide. So why aren't all oxides passivating? That's our next question. Yeah, Hayden.
Don't some shells that get created are too thick and too small to actually function correctly?
Oh, you're on the right track.
Yeah.
Too small isn't necessarily a problem, but they can get too thick, and then what happens? Let's do Ryan. Right. Oh, Zachary, I'm sorry.
Wow.
Names. You work in my group. I should know that.
It's just too porous.
Yeah, some of them, instead of like, imagine like your block of cheddar cheese, that's a solid block. That's a dense metal oxide block. But then you got your Swiss cheese with like holes running through it. So gas can still get through that layer. So some things actually form a porous layer. If it's porous, then the metal and the oxide will keep on corroding. What else can happen? There's one other thing. We've already done some questions. Let's do, you remind me your name? Connolly.
If it grows too fast, then it can crack and fall off.
So the rate isn't always the biggest thing, but yeah, it's the strain. When you grow this oxide, the way that I drew this, the metal oxide layer is basically it matches the metal underneath. But what if when you grow it, let me just move this down, give myself a little more space. Imagine now that you've got this, a metal, and when it grew on the metal, so this is your metal oxide, and when it grew on your metal, it's bigger. It just takes up more space. Then when that grows, it's going to be strained. And we know that ceramics, because metal oxides are typically ceramics, right? Because ceramics don't tolerate strain, something we'll learn a lot more about in a few chapters. It can't just be squeezed very easily. Instead, it's going to spall off. Spall off is when a scale comes off, and you've seen this. In fact, we've got it. Where do we have the iron? So this. We'll see in a moment what happens when what it looks like when it spalls off. Okay. So how do you know whether or not a metal is going to spall off, be dense, be porous? How do you do that? We have a great tool. We have what's called the Pilling-Bedworth ratio. And what we really want to know with the Pilling-Bedworth ratio is what's the ratio of the oxide that forms to the ratio of the metal, right? The ratio of the oxide to the metal. That's what we care about. If they're basically the same, if they occupy the same volume, then there won't be any strain generated and there won't be holes left in it, right? Both of those things cause this thing to keep on rusting, right? So to calculate this, you need to figure out the volume. We know how to get volume. We just take what? If you want volume, how do we get that from density? How does density and volume relate again? Yeah, density equals mass over volume. So if you want to solve for volume, you'd say that volume is equal to the mass over the density. So that's what they've done here. You've got oxide, the mass of the oxide. This is going to be the molecular weight, right? The grams per mole molecular weight. The molecular weight of the oxide times the density of the metal multiplied by the number of electrons involved in the redox reaction and then the molecular weight of the metal times the density of the oxide. If you punch all these values in, that will give you this ratio of the volume of these two oxides. And then we just plug it into these rules. We say if the Pilling-Bedworth ratio is less than 1, if it's less than 1, then what will happen? What will our layer look like if it's less than 1? It will be, is it porous? Let's see. Yeah, that is porous, I think. Then it is porous, and if it's porous, then the oxygen has a pathway to get to the metal surface. You just keep on corroding. If it's greater than 1, right, Ce, like ceria or cerium and cerium oxide, what about that? Yeah, we should say, I should add this, I should say that it is greater than 1 but less than 2, right? In that case, we call those passivating, meaning it's a pretty close match, and so it's going to be relatively dense. It doesn't mean you can grow the oxide, infinitely thick. It might only survive a micron thick or a few nanometers thick, depends, but it'll stay put, right, up to a certain thickness, and in that case, it's going to be passivating. But if your Pilling-Bedworth ratio is greater than 2 or 3, it's going to spall off. That basically means that the oxide is much larger than the metal, and it's just too much strain, it's going to spall off. It'll chip off and expose new metal underneath it, right? So this is spalling occurs. So the first and the third scenario both cause continued oxidation, and the second one doesn't. And so if you were actually to plug in your Pilling-Bedworth ratio for a bunch of different metals, you'll realize why some things corrode easily and some things, even though thermodynamically they look like they want to corrode, they don't, because they're kinetically limited, because you just can't get ions to transport through this layer. Okay? Any questions on the Pilling-Bedworth ratio? Brandon?
So, even if something is porous, there's a thicker oxide layer will eventually passivate just through the shear thickness of the oxide layer?
Okay, well, the rate will change, and that's actually a good segue, because that's what we're talking about next, is the weight gain, right? So if you take a piece of iron and you expose it to just air, right? You set it on a scale and you form an oxide, then you're adding oxygen and it's reacting with the metal. So overall, your weight should be going up. You're taking what was pure iron before and you're converting some portion of that iron into iron oxide. So the weight should be going up. So you could actually monitor weight gain this way. Let's do 2 questions. Yeah, Thomas?
Does this class ever cover the bond strengths between metal oxides?
The sort of like the bond between the oxide and the metal underneath?
Yes, sir.
Not exactly. We offer a ceramics class if you want to learn more about that. An introduction to ceramics, which I think people would generally enjoy. I used to teach it. I think it's great. You can learn more about it in there. Jeff?
What about the N? Oh, I see it there. Number of metal atoms. Okay, sorry.
Yeah, the number of N is the number of metal atoms in the metal oxide.
Why does that matter for the metal and not for the oxide?
Oh, I think I said number of electrons. I'm sorry. I think I stated N is the number of electrons. N is the number of electrons in our previous equations. Here it's the number of metals here. The reason why is because let's say you're starting out with vanadium metal and it goes to vanadium 205. You need 2 moles of vanadium to convert it into V2O5. So that's what that's taking account of. Other questions? Yeah, Rob?
Sorry, so you said N was what number of metals?
Is the number of metals atoms in the metal oxide.
Metal atom.
Yeah. So if it's Al2O3, N is equal to 2. If it's TiO2, N is equal to 1. Okay. So weight gain. You can monitor this weight gain as a function of time. Let me give myself a little space. If you were to plot mass gain as a function of time, you can see different behavior. You can see one where it goes sort of like that. You can see one where it's linear. You can see different dependence, right? And the different dependence dictate, it can tell you something about the oxide that's forming. For example, if it's parabolic, if you can fit it with a second order polynomial, that often implies that you have a non-porous oxide that adheres to the surface, where ionic diffusion then dominates. Ionic diffusion is, again, when these ions have to transport through this layer. Parabolic is basically it's getting slower when that happens. Another one you've got is if it's linear, meaning as a function of time, the oxide just keeps growing at the same rate, then that means spallation is occurring, or that the oxide is really porous. Because in either case, oxidation is just continuing at roughly the same rate, right? And then logarithmic is observed for very thin, low temperature oxide formation, and alumina is a great example of that. Okay? And I just want to plug that if you have more questions on thermodynamics or electrochemistry, there's some great resources. Here's one from Purdue that I actually liked quite a bit. They have a ton of worked example problems. Today we're going to work just a couple quick example problems on this in preparation for the exam next week. The first one is the following. If you have 2 moles of SO2 gas and you combine it with oxygen to form 2 moles of SO3 gas, right? So all your species are gases. The question says, if the equilibrium constant K, now what is K? We've been writing delta G equals delta, I should put my R's for the reactions, delta RG naught plus RT natural log of Q. So what is K? We use K instead of Q, or rather it's the same thing, but K is a special case of Q at equilibrium. K is Q at equilibrium. Right? So I could have said Q, but when we use the word K, it just implies, okay, this is a special scenario. This is when the reaction is not going forward or backwards. It's when it's staying put, right? So we're told what the equilibrium constant is. We say that it's 10 at 960 degrees Kelvin. And then it says calculate delta RG and indicate the direction of spontaneous reaction if initially we have these conditions. So calculate delta RG, whether or not this reaction goes forward or not, if you have these conditions. So those conditions do not correspond to a K of equal to 10. I give you K equals 10, and then I say, all right, if we change our initial conditions to have that, will the reaction go forward or backwards? So let's do this. Let's do this now. You're going to put in your answer in kilojoules. So just type in the number. You don't need to type kilojoules. But for this clicker question, you'll be putting in the answer and make sure that your units are kilojoule per mole, but you don't need to type those units in. You're just going to type in a number. Right? If you think the answer is 80 kilojoules, just type in 80. Okay, Rosa, question?
So are you saying that we are going to use value K for Q, or we're not going to?
With this information, I've asked you to find out if these were your initial conditions, and you know that if this were under equilibrium, that's what that is, under these conditions, will it go forward or not? So think of this as background information that you're going to need to solve this question. Should we get started on this together? Let's get started on this. This one's a little bit challenging. So anybody have a thought where you might begin on a question like this? Hayden, what do you think? Where do you start on something like this? Okay, so it's asking us to solve for this. And before we can solve for that, we need to know Q, which we could figure out, right? Because we have these things. We could write our reaction quotient. We could say that Q equals products over reactants. So it's going to be the partial pressure of SO3 squared over the partial pressure of O2 to the 1 power, partial pressure of SO2 squared, right? And since you have values for those, you can get a value for Q, right? Equals some number. Then what do? Because now you don't have delta RG naught, so how can you solve for delta RG? That's the problem you run into in this question. So how do we solve for delta RG naught? What strategy? What do you think, Tyler?
Well, I think we use delta G equals 0 at equilibrium, and then you use LMK.
Bingo, that's it. When I say that the equilibrium constant is given, that tells you something. What happens at equilibrium? What can we set to 0 in this equation? Delta RG. Not delta RG naught, but delta RG. We can set that equal to 0. So at equilibrium, delta RG equals 0, right? And then you plug in K for Q. That will allow us to solve. So use K to solve for delta RG naught. Okay, once you know delta RG naught, you can go back and you can solve for delta RG with this value of Q. So get started on that one and raise your hand if you need some help. We got some TAs that can give you a hand.
The answer you wanted, we're finding
I had a good question. Somebody said, for these values, are those partial pressures or those actual pressures? And I don't remember. So at the end of this class, I think that they're partial pressures. What I can do though for this clicker question, I can make it so that either answer you give, incorrect or correct, is still worth your points. So don't worry about points. But I would assume that these are partial pressures. I just can't remember what I did on this one. Yeah, actually I'm pretty sure that they're partial pressures.
Kilojoules per mole.
Okay, we'll do maybe 2 more minutes and we're going to wrap this one up. Okay, another 30-ish seconds. The units should be kilojoules per mole. So if your answer comes out to be, 50 kilojoules per mole, just type in 50. Okay, get your answers in. Another 15 seconds. Don't sweat it. This is just worth a point. If you haven't gotten it, phone a friend if you're desperate. Okay, we're going to end it. Answers in, answers in. What is the right answer? Let's see what we get. Okay, so the correct answer is negative 42.3. So most people are getting that, and maybe half are not. Well, actually, so 40% of people are getting it, right? How did we get this? What I'm going to do is, since we only have 10 minutes left of class and I have a neat demo I want to show you guys, I'm going to work through the rest of this one in a video and post it as a homework solution video, right? And I'll do it for another problem as well as an electrochemistry problem. So those will be available. I'll just do those later today. For right now, I would like to switch and talk about this demo real quick. In this demo, we've got a piece of iron wire stretched between two posts, and we've got it pretty snug. What I'm going to do is I've got them connected to electricity, right? This is going to go into the wall. This machine here is called a variac. It's a transformer, basically. It changes what the wall spits out to go between 0 and 100% of what the wall spits out. So if I have it set to 0 right now, it's not getting any voltage. So somebody tell me, if I've got my positive and negative ends hooked up as they are on this piece of iron wire, what will happen as soon as I turn this dial and start giving this thing some juice? I'm going to start sending current through it. Now, it's not a DC current. It's not like I'm going to send electrons just one direction. Instead, AC, alternating current, means that it's switching. How fast is it switching? 60 hertz, which is how fast? 60 times in 1 second. So 60 times in a second, it's switching whatever the voltage is that this thing is putting out, right? And this value can be all the way up to 120 volts if I were to crank it, right? So what will happen as soon as I start to do it? Current starts to move around. What should we actually see? Will it start to vibrate, maybe? Spin, I think someone said. What else? See it? Yeah, here's another thing. This is a magnet. It's a little magnet sticking to it. Right? This is just a weight. You can ignore that for a moment. I used that just because it won't melt. Right? So let's actually see. I'm going to turn out some of the lights because it's easier to see with the lights on. So I'm going to heat this up. I'm going to take it up to 15%. So it's getting 15% of the power. First off, you see that smoke occur. When I look at the height of this thing, I see that it's currently it was at almost 10 inches when I read on this ruler, but it's actually dropping. That value is dropping below. It's almost down to 9 inches now by that weight. So it's drooping. Why is it drooping? Magnetic field? Nope. What's happening? Resistive heating. I'm passing a current. I'm jiggling the electrons around in there, and they're bouncing into atoms and imparting energy as they do so. So it's heating up, and it's getting longer because things expand. Almost all things expand when you get them warmer. So that makes sense that it's drooping. Now, what will happen if I crank it up to, say, like 30? Anything? Well, first off, what was the smoke all about?
Oil on the wire.
Why did they put oil on the wire? Because it's iron. It's not stainless steel. This is iron wire. Iron rusts really easily. Its Pilling-Bedworth is one that it produces an oxide scale that just keeps on growing. So if you're going to sell this stuff, which you can only buy at Joann's, I found out, after searching many at Home Depot, you can buy iron wire at Joann's, right? It comes in oil, so it actually makes your fingers look gross. That oil was gone as soon as we passed some current through there because it burned pretty easily. All right, let's take it up to 30 and see what happens. It's really drooping. You see how much it's drooping, right? It's down to it's down to 8 inches, so it's dropped 2 inches down, and we see some color change now. Why is it changing color? Because it's getting quite warm, right? Now, why are certain spots brighter than others, right? If you notice, like, it started to change here and then over here, why didn't it change uniformly? Any thoughts? Different parts of it, what happens is this wire, because it's rolled up in a coil like this, parts of it have little bends, right? Every time you bend a wire, you introduce what's called a dislocation, something we'll talk a lot more about in this class. And those... Oh, dear. Did you see that? Yeah.
Yeah, it's like.
Must be slightly conductive. I haven't seen that happen before. Okay, I lost my train of thought with the thought of para. So I'm going to turn up just a little bit. I'm going to do less than I normally do because I don't want to hurt myself or anyone else. Right, we're going up to 35, up to 40, right? Parts of it that, the dislocations, they resist electron flow, and that causes heat to generate faster there. So this is getting quite hot. If I keep heating it, nothing terrible happens. I don't want it to melt, I don't want it to, but I do want that magnet to drop. If we keep on heating it, that magnet should drop her up above 40, which is frightening. Definitely not touching it. That's 60 volts, which I do not want going through me. If you heat it up, that magnet will eventually drop. Let's go to 50. If it doesn't drop at 50, I'm just going to tell you that it will drop eventually because I'm a little bit worried today. There it goes. It dropped. Now watch this. That's not even the cool part. Watch this. I'm going to kill it. What will happen when I kill it? It just goes back up. Or will it? Up, down, up. So what on earth happened, right? It made sense when you heated up, the hotter it got, the more it expanded, the more it drooped. We saw something funny. Yeah, we saw Twilight music going on, X-Files, right? We saw that it expanded, and when it was heating up, you didn't see it because it happened slowly. But as it was getting lower, it must have slowly gone up and then gone down again. But we saw it really clearly when we killed the power, because it starts cooling off quickly. It went up, it went down again for a minute, and then it went back up. And at the beginning of next class, we will explain what on earth is happening.
Good question.